Hello everyone, it's Steve with Aptera Owners Club. In this video, I want to talk a little bit about sodium-ion batteries. We've been hearing a lot about sodium-ion batteries for the past several years, ever since KATO put out that announcement that they're going to be commercially releasing a sodium-ion battery in 2023. But sodium-ion batteries have been around for a long time, since the 1970s, but because of issues mainly of low cycle life, they just couldn't be recharged very often. People kind of gave up on them, and lithium became the dominant chemistry. But if you look at it, lithium and sodium are very, very similar because they are both alkali metals. So they both have one electron in the valence shell. And the only difference between lithium and sodium, well, the major difference is that sodium is much bigger. So it's bigger and it's heavier than lithium. So significantly heavier, significantly bigger. Um, but the other major difference is that lithium is fairly expensive and sodium is quite abundant and very cheap. Right now, large lithium sources are only available in a few countries in the world, but sodium is kind of universally available and it's much cheaper. So there's a lot of advantages to sodium ion batteries. And usually I'm not really that big into this future tech because most of the stuff that people talk about is just way off in the future, kind of like solid state batteries are probably not happening anytime super soon. But this looks like it is going to go to commercial scale next year and very soon because a lot of companies are into it and they've partnered with either they are themselves big companies like KATL, or they've partnered with big companies that have manufacturing know-how and know how to scale. So there's a lot of advantages. One is we know that in the EV sector, we're going to need about 500% more capacity within the next several years. And it's just going to be hard to extract that much lithium. And extracting lithium is pretty hard on the environment. It's very resource intensive. And you have to source it from a few countries around the world. Sodium, again, less resource intensive to get, much cheaper. So it's a factor of like 100 times cheaper, the raw materials. Now that doesn't mean that the batteries are going to be 100 times cheaper because the cost of the elemental lithium or the sodium is a relatively small portion of the total cost of battery manufacture. So they suspect that the cost will be about 20 to 40% cheaper than a comparable lithium-ion battery. But that is one major cost: ease of access to the raw material, and it's much cheaper and it's less toxic to create the battery, because when you make lithium ion batteries, you have to use fairly toxic solvents to do the liquid phase manufacturing, and you can use less toxic solvents for the sodium ion batteries. Then next, safety. There's no risk of thermal runaway. Lithium ion batteries, depending on the chemistry, are more or less safe. But none of them are as safe as sodium ion batteries. And in fact, sodium ion batteries, you can deplete them to zero. You can run them completely down to zero. You cannot run a lithium ion battery completely down to zero. That's an unstable state for it. But you can run sodium ions all the way to zero, and then you can transport them. There's zero risk of them catching fire when you run them down to zero. So for transporting large quantities of batteries, it's very safe. The other major advantage is it works great at low temperature. So down to negative 20 degrees Celsius, it retains most of its performance, which is really great news for EVs in colder climates. So you don't have to warm up the battery. It works great from a range of negative 20 to like plus 65 Celsius, which is pretty hot, much higher than ambient temperature anywhere in the world. And then it's highly recyclable. And it has yet to be manufactured at commercial scale, but the manufacturing process is very similar to lithium-ion batteries, and it's very easy to convert a lithium-ion battery manufacturing plant to a sodium-ion because many of the processes are extremely similar and the machinery and the equipment you need are essentially the same. Now, the biggest problems with sodium-ion batteries is that their gravimetric energy density is quite low. 70 to 160. Potentially, you can go to 200 watt hours per kilogram. KATL has claimed that they have reached that. That's still significantly less than, almost 300 watt hours per kilogram for NMC batteries, which is what Aptera is going to use. And but it is likely that sodium-ion batteries will surpass lithium iron phosphate gravimetric energy density. And lithium iron phosphate is actually pretty good. So that is not that big of a problem unless you want, the most dense battery that you could possibly have. For something that's really efficient like the Aptera, lithium iron phosphate or sodium ion would probably be fine. The other big problem was cycle life. It just doesn't have the longevity and cycle life of lithium-ion battery. But this is the area that they've made the most headway into lately. And they are approaching lithium-ion battery cycle numbers. And in some cases, depending on the type of battery that you're using, they have surpassed it. So how does it differ, and how's it similar to lithium-ion battery? So we're going to go back to this schematic about lithium-ion battery. So on a lithium-ion battery, the current collector on the cathode is aluminum, and the current collector on the anode is copper, and the anode is usually graphite. Now, and then the lithium-ion ions intercalate between the graphite. Now, the problem is that the sodium ion is much bigger than the lithium ion, so therefore it can't intercalate into graphite. So you cannot use graphite in a sodium ion battery. They end up using what they call hard carbon. Well, it's essentially like charcoal, and so they use that instead. And then the electrolytes are a little bit less toxic than used in lithium ion batteries. So other than that, they're pretty much the same. The manufacturing process is the same. And the three major companies that are doing it are Faradion. I don't know if I'm pronouncing that right. And then Natron Energy. This is an offshoot of a research group out of Stanford. So this is based out of the Bay Area. And then KATL, which is the largest battery manufacturer in the world for lithium-ion batteries. And they're the one who made the announcement back in 2021 that they will be releasing its first generation of sodium-ion batteries in 2023. And so the new information is that Faradion, which is a small UK company, and they're the longest. They've been working on these sodium-ion batteries for the longest time out of any of these companies. They were recently bought out by an Indian company, and let me see if I can find the name of it. Oh yeah, Reliance Industries. So Reliance Industries, at the end of 2021, bought out Faradion for $136 million. And they are planning to build several gigafactories in India by 2024 to produce these. So Reliance is putting a bunch of money. They're a very large conglomerate, Indian conglomerate, and they're putting a bunch of money into that. And then KATL has said it, and as we know, KATL is the largest. And then Natron is that company that's based on out of Stanford's research group. Now, they have a different chemistry that uses Prussian blue for both their anode and cathode, rather than a lot of the places use Prussian blue for the cathode and then use hard carbon for the anode. Their volumetric density is quite low at 70, and they're thinking about using their battery more for like a grid storage system. But their advantage is that their cycle life is ridiculous. So lithium-ion batteries in the several thousand, they claim their cycle life is in the hundreds of thousands. If they were to improve their volumetric density to be used in a car, this could theoretically make a car have millions of miles of lifetime use before their battery goes out, like several million. So it's like way overkill. Their cycle life is huge for their technology. KATL is claiming that they're going to reach 200 watt hours per kilogram, which would be slightly better than lithium iron phosphate batteries. So we'll have to see about that. And then Faradion, I think they've reached like 180 watt hours per kilogram. And the most exciting thing, I think, out of all this is there's research going on right now that's talking about designing a cell for sodium-ion batteries that's fully recyclable, and you can recycle greater than 90% of its components very easily. And they're using a chemistry that's sodium vanadium phosphate. And what they do is, after it's done, they can just do this recycling in a 3-step process. There's a small video about it that we can kind of watch. I don't know that this is going to reach commercial scale, but basically at the end, you take the cell, you crack the cell open. And so the advantage of this is when they try to do this with lithium-ion batteries, the problem is that the copper current collector and the aluminum current collector, they react with the lithium and the other components inside of there, and it's very hard to separate those two once they react. With the sodium ion, you can use aluminum for both the cathode and the anode current collector. So yeah, here we go. They just put it in there. They put it in just pure water, and then the sodium reacts and becomes sodium hydroxide. And so yeah, on these things, you can use aluminum for both ends. And as they shake it, the sodium hydroxide in there reacts with the aluminum foil and makes aluminum an aluminum oxide. Then and then the other thing that's good about sodium ion is you don't actually need cobalt or lithium either, because those are the other components that are hard to get. It's hard to get cobalt, it's hard to get lithium. Oh, excuse me, hard to get nickel. So a lot of these don't use nickel. They use like iron and manganese rather than nickel and cobalt. And iron and manganese are easier to get at. So they precipitate this out after it reacts, and that black material in there is what's left over, the vanadium. And in this liquid phase is the aluminum. And then like the casing materials are also inside there. Yeah, so this is the sodium vanadium phosphate slurry, which and then this is the components. This is the sodium aluminate solution. Then they're going to add hydrochloric acid into here and turn this into aluminum hydroxide. And then aluminum hydroxide is basically like aluminum ore, and they can extract the aluminum out of there fairly easily. Okay, so it's like a very recyclable and easily recyclable battery, which I think is also a huge advantage to this thing. So yeah, I'm pretty excited that Kate, there's 3 companies that are bringing this to market, and it looks like this could go into commercial production as early as next year. Now, initially, I think the gravimetric energy density makes it so that it's not very attractive to cars, at least high performance cars. I think initially you're going to see a lot of these in like e-bikes, scooters, and lower end EVs and electric cars in emerging markets where cost is more important than range, because these aren't going to have great range and because of how much density it is, but they're going to be significantly cheaper. Just think if the batteries were 40% cheaper in an EV, that's like the largest cost in EV usually is the battery pack. So that would make EVs very cheap across the board. And eventually, once they get these energy densities up to 200 watt hours per kilogram, I think we're going to start seeing them more in more and more EVs. And because of the new law that passed, that you need to source the materials from certain countries in America to get the tax credit, sourcing the nickel and the cobalt and the lithium are all going to be difficult. But sourcing manganese, iron, and sodium is going to be pretty easy. So that's another thing that has sodium ion going for it. I'm fairly optimistic about this technology more than the other battery technologies that people talk about in the future. So I think we might see these in the next 5 or 6 years in commercial products. All right. Well, I hope that was interesting and helpful to you guys. Any comments? I'd love reading your comments below. Thanks, as always, to our supporting members who are on the screen here. And have a great day, everyone.